The development and deployment of atomic bombs represent a pivotal point in human history, marking the intersection of science, technology, and the devastating potential of nuclear energy. From an engineering standpoint, the creation of atomic bombs involves intricate processes that harness the fundamental principles of nuclear physics. This essay explores the engineering aspects behind atomic bombs, shedding light on the key components and the scientific principles that drive their functionality. At the core of every atomic bomb lies the principle of nuclear fission. Engineers design these weapons to initiate a self-sustained chain reaction where heavy atomic nuclei, typically uranium-235 or plutonium-239, split into smaller fragments, releasing an enormous amount of energy. Achieving and controlling this reaction necessitates precision in the design and manufacturing of the bomb's fissile material, ensuring optimal conditions for a rapid and efficient fission process. One engineering challenge in atomic bomb design is achieving the necessary conditions for a critical mass to trigger the chain reaction. Many bombs use implosion design, where conventional explosives compress the fissile material into a denser configuration, effectively reaching critical mass. Engineers meticulously design the implosion system to achieve uniform compression, minimizing the risk of a premature or asymmetrical detonation, which could lead to reduced efficiency or failure. Initiating the explosive chain reaction requires advanced engineering solutions for the bomb's initiator. Neutron initiators, often incorporating polonium and beryllium, play a crucial role. Engineers carefully calibrate these initiators to produce a burst of neutrons precisely at the right moment, triggering the rapid fission of the fissile material and ensuring an explosive release of energy. Beyond the internal engineering challenges, the delivery systems of atomic bombs demand careful design. Ballistic missiles or aircraft serve as carriers, requiring engineers to address issues of stability, aerodynamics, and guidance systems. Precision is paramount to ensure the bomb reaches its intended target and maximizes its destructive potential while minimizing collateral damage. To prevent accidental detonation, engineers incorporate intricate safety and arming mechanisms. These systems involve interlocks, safing devices, and fail-safes to guarantee that the bomb activates only under specific conditions. This engineering aspect is critical for ensuring the controlled deployment of atomic weapons and preventing unintended consequences. While engineers contribute to the technological advancements of atomic bombs, ethical considerations are essential. The destructive power of these weapons necessitates a careful balance between technological innovation and moral responsibility. Engineers must grapple with the implications of their work, considering the broader impact on humanity and global stability. The engineering of atomic bombs involves a multifaceted approach, encompassing nuclear physics, material science, and aerospace engineering. While these technological achievements showcase human ingenuity, they also underscore the ethical dilemmas associated with harnessing such destructive power. As we reflect on the engineering behind atomic bombs, it becomes imperative to channel our collective knowledge and skills toward promoting peace, diplomacy, and the responsible use of technology. Who was Oppenheimer? J. Robert Oppenheimer was an American physicist born on April 22, 1904, and he passed away on February 18, 1967. He is widely recognized as a key figure in the field of theoretical physics, renowned for his significant contributions and leadership role in the Manhattan Project. Oppenheimer received his education in physics at Harvard University, where he later completed his doctorate at Göttingen University under the supervision of the German physicist Max Born. Following his academic pursuits, he became a professor at the University of California, Berkeley, where he published a series of influential papers on topics such as the structure of the atomic nucleus, neutron stars, and quantum electrodynamics. However, Oppenheimer's legacy is perhaps most prominently associated with his involvement in the Manhattan Project during World War II. The Manhattan Project was a groundbreaking initiative aimed at developing nuclear weapons for the United States. Oppenheimer played a pivotal role as the scientific director of the project, overseeing the scientific aspects of the development of atomic bombs. The successful outcome of the Manhattan Project marked a turning point in history, ushering in the era of nuclear weapons. Despite his instrumental role in advancing scientific knowledge, Oppenheimer's legacy is also marked by ethical and moral considerations surrounding the use of atomic weapons. After the war, he became an advocate for international control of nuclear weapons and served as the chairman of the General Advisory Committee of the newly established United States Atomic Energy Commission. J. Robert Oppenheimer's life and career reflect the complex interplay between scientific advancements, wartime exigencies, and the moral responsibilities associated with groundbreaking technological developments. The atomic bombing of Japan. The atomic bombings of Hiroshima and Nagasaki in August 1945 were pivotal events that brought about the end of World War II. The decision to drop atomic bombs on Japan was a highly controversial one, made by President Harry S. Truman, with the aim of compelling Japan to surrender and avoiding a protracted and potentially costly invasion of the Japanese mainland. The first bomb, codenamed Little Boy, was dropped on Hiroshima on August 6, 1945. The impact was catastrophic, instantly killing tens of thousands of people and causing widespread destruction. 3 days later, a second bomb, Fat Man, was dropped on Nagasaki, further amplifying the devastation. The unprecedented scale of destruction and loss of life underscored the terrifying power of nuclear weapons. The bombings had a profound and immediate effect on Japan's leadership. Faced with the overwhelming force of atomic weapons, Japan announced its unconditional surrender on August 15, 1945. The post-war period marked a significant shift in Japan's trajectory, as the nation underwent reconstruction under Allied occupation. While the bombings achieved their immediate objective of ending the war, they also sparked intense debates about the morality and long-term consequences of using nuclear weapons. The events of Hiroshima and Nagasaki continue to serve as a somber reminder of the devastating impact of nuclear warfare and have left an indelible mark on global history, shaping discussions on nuclear disarmament and the ethical considerations surrounding the use of such powerful weaponry. In contemporary times, the perception of atomic bombs is deeply nuanced, reflecting a combination of historical, geopolitical, and ethical considerations. While the devastating impact of the atomic bombings of Hiroshima and Nagasaki during World War II remains imprinted on collective global consciousness, the prevailing sentiment is generally one of aversion towards the use of nuclear weapons. The potential for unparalleled destruction, loss of civilian lives, and long-lasting environmental consequences has led to widespread acknowledgement of the catastrophic nature of atomic bombs. International efforts, such as the Treaty on the Non-Proliferation of Nuclear Weapons, NPT, underscore a commitment to prevent the spread of nuclear weapons and encourage disarmament among nuclear-armed states. However, the existing nuclear arsenals of certain nations and concerns about the proliferation of such technology contribute to a complex global discourse. Additionally, advancements in nuclear technology for peaceful purposes, such as energy production, further complicate the perspective on atomic bombs, as the dual-use nature of nuclear programs raises questions about the potential misuse of technology originally developed for non-military purposes. In this contemporary context, there is a growing emphasis on diplomatic initiatives, arms control agreements, and global cooperation to mitigate the risks associated with nuclear weapons. The perception of atomic bombs today is shaped by a delicate balance between the acknowledgement of their destructive potential and the ongoing efforts to prevent their use through international collaboration and disarmament initiatives.